question paper 1, 2. Just a second. Question paper 1, 2. Just a second. So this one we were at 28, question 28. Copy. Sorry, this is not the paper. We were just 1 second. Let me quickly open the right paper. 5-2 खुल गया. अच्छा 1-2. अच्छा this paper question 28. ठीक है. अच्छा, we were at this point, and I think we had done question 27. अच्छा, question 28. Moving to question 28. The diagram shows a carboxylic acid P, and it said maybe formed from X, Y, or Z. So you have carboxylic acids getting formed, and remember how are carboxylic acids formed? I'm going to take an example of ethanoic acid. They're formed by 3 things. You have a primary alcohol like CH3, CH2OH, which is ethanol, and that would turn into a carboxylic acid, CH3, COOH. That is oxidation. An aldehyde would pretty much do the same thing. Like you have an aldehyde, double bond O and H, CHO. That would be oxidized by tolerance K2Cr2O7 or by felling. An aldehyde would get oxidized to a carboxylic acid as well. And the last one was that a nitrile pretty much does the same thing. You have a nitrile, and nitriles have 2 hydrolysis. There is alkaline hydrolysis and there's acid hydrolysis. Uh, After hydrolysis, nitriles would also turn into a carboxylic acid. But if it's alkaline hydrolysis, remember कि alkaline hydrolysis mein what happens is that the carboxylic acid would in return react with the alkali. So you won't get a carboxylic acid, you'll get a salt of the carboxylic acid. So which row is correct? The first one is the alcohol is definitely primary. Because carboxylic acids are only formed from primary alcohols. I mean, this entire reaction, it only happens for primary alcohol, so it's primary. And the change in MR is greatest for, you can figure out the change. I mean, the change is going to be pretty much the same for each one of them. So, yahan pe the change is, what is the change that's happening? I mean, what's the difference between these two? Let's try and figure out the change. I think there's, the CH3 part is the same, CO, there's an addition of O. So that's 16. Achha, yahan pe what is the change that's happening? What's happening over here is the CH3 part is the same, and what's changing is that 2 hydrogens are getting lost, and instead 1 oxygen is getting added. So that's 1 oxygen getting added, that's 16, and 2 hydrogens getting lost, that's -2. So that's a change of 14, I think. And you can correct me if I'm wrong. Over here, what's happening over here? There's an N getting lost, so that's -14. Plus there are 2 oxygens, that's 32, plus 1 hydrogen that's getting added. So what is this? 33 minus 14. Kya hota hai? What is 33 minus 14? That's 19. So I think the greatest change is Z to P. ठीक है? Is this clear? Rida, Heba, is this clear? Abba, is this clear? Achha,
Yes.
next is There's a molecule compound R is shown, and it's obviously an ester because there's this ester link. What is the name of the compound R, and how does its boiling point compare with that of butanoic acid? So butanoic acid is this thing. Can somebody tell me which one is going to have a butanoic acid? Is this thing C double bond O, and there's going to be OH, and this is CH2. Can anyone tell me why? Who's going to have the higher boiling point, and why would it have a higher boiling point? Can somebody answer both things?
Sir, I think butanoic acid would have the highest boiling point because it has hydrogen bonding.
Okay, because of the OH, it's a highly polar. I mean, the H is positive, and the O has lone pairs, which are strongly partial negative. So it has hydrogen bonds. It's capable of forming. It's capable of forming hydrogen bonds. So it has the higher boiling point. That's correct. Uh, Plus, what's the other one? अच्छा, the name. That's the name. अच्छा, पहले तो वो कर लेते हैं. Okay, it's going to have a boiling point it's either this one, B or D. अच्छा, what's the name of this molecule? Just a second. I've lost. अच्छा, what's the name of this molecule? Okay, esters are named in two parts. An ester is going to be named in two parts. This is the side where it's going to be meth. There's only one carbon atom, and the other side is going to be it has a total of three carbon atoms. That's prop. ठीक है, तो वो आपका prop है. The carboxylic acid side is known as O8. ठीक है, so it's going to be methanoate. And the single O side, the alcohol side, would be your alkyl. It's going to be vinyl. So it's propyl methanoate. So the answer is going to be D. ठीक है, Zahib, is this clear? Tala, is this clear? बाकियों clear है?
Yes, sir.
Yes, sir.
So then the next part is it's the infrared spectrum. ठीक है, the bonds they vibrate randomly at different frequencies by absorbing different frequencies. So if you look at this molecule, there's this frequency that's getting absorbed. There's a frequency getting absorbed over here. Some random frequency getting absorbed over here. And he's saying what could be Q. So there are four options given. And we have to figure out, we would need a data booklet. The first thing is I would need to draw these molecules. Butan 1-ol is four carbon atoms and it has an OH bond. Okay, all the rest are hydrogens. Okay, so these are all hydrogens. What's butanoic acid? That's four carbon atoms, a double bond O. Okay, so there's a double bond O and an OH. And the rest are all hydrogen atoms. What is butanone? Butanone is going to be four carbon atoms with a double bond O. And the rest are all. And what's 3-hydroxybutanol? Butanol is an aldehyde, which means a double bond O and an H. And 3-hydroxy, which means what is hydroxy? Hydroxy is an OH group. So it also has an OH, and these are your hydrogens. Now remember, when you look at an NMR spectrum, and I would need a data booklet to go with this. Just one second, quickly. ये खुल जाए एक second. No idea why it's slowing down. So I'm just going to answer this. over here. Okay, we can confirm when the data booklet is open. Remember this thing, you don't get a lot of information from the data booklet. Uh, there are few bonds that are very uniquely identifiable. So remember, there's this absorption at 1600 to 1700. You don't even have to. I mean, you're going to waste time in your MCQs if you even refer to the data booklet on this. Remember this absorption. Okay, just memorize this. Around 1600, 1700, if you get a very strong absorption, that's a serial bond O vibrating or stretching or twisting and absorbing this particular frequencies. Okay, so that eliminates the first one because it doesn't have a double bond O. The others, they have a double bond O, all of them. I said then another thing that needs to be eliminated is the OH. There's not going to be any OH. Let me see if the data booklet is open. It's here. I said the other thing that's uniquely identifiable in your infrared spectrum, and that is your OH. Okay, this one over here. The OH bonds are very uniquely identifiable because they have an absorption at around 2500. Now, carboxylic acid is gone because it's going to have a very broad absorption. So we can eliminate carboxylic acid. That's what I'm going to do. So the carboxylic acid, जो हमारे the options that we had. So I'm going to get rid of the carboxylic acid. You can't have an OH in the carboxylic acid because it has a strong and broad absorption around the 300 mark. You don't have a broad absorption. A broad absorption is a very wide absorption. So that's not happening. So that is gone. The other alcohols, they have an absorption at 3200 or above 3200, around 3500. We don't have that, and they have a strong and a sharp absorption, but it's much higher than 3000. If we look at our graph, then ours is approximately at 3000, and it's not a very strong absorption. It's probably just an average absorption. So no, that would indicate that there is no OH. So that would eliminate this one because it had an OH. It would eliminate so all the others eliminated. So you're left with this one only. Okay, this is the only one that's left. So it's going to be butanone, and we're definitely getting other absorptions. So this one is definitely not OH, but there's this absorption around 1300. Let me just have a look at the 1300 mark. So we have a strong absorption at the 1300 mark because of C single O. So we are getting. So the problem is this is suggesting that there is a serial bond O. This one because there's this absorption around the 1200 mark. So if there is a serial bond O, this one is kind of then doubtful because remember the frequency absorptions are not always exactly where they should be. They always have a range. Now the problem is if you want a C single O in it as well, you would have to get rid of this. I mean, this doesn't have a C single O. This one has a C single O. I mean, it has both things. It has. So I need to go back to this because we found a C single O absorption, and there was a C double bond absorption, C double bond O absorption as well. This one is confirmed eliminated because it should have a strong and broad P absorption, but that's not there. This one is eliminated because there is no C double bond O, so we are confused with these two now. C double bond O is there. There's a strong absorption at around 1600 to 1700. But we were getting other strong absorptions. One is at the 1200 range. So there's a pretty strong absorption, and the data booklet suggests that there's a C single O. Now, if there's going to be a C single O, then you would have to get rid of this one. because this one doesn't have a C single O. This one does have. So that would leave us with the OH confusion because I had suggested that this was not OH. But the problem is that all the other peaks are matching except for the OH one. Now, the OH peak for an alcohol is around the 3200 and 3600 range. But our peak is, in our case, is around the 3000 mark. Now, considering the fact that there might be some variance because absorptions are always have a range and the molecule looks different, maybe I can go with an OH. Maybe I can accept this as an OH, mainly because of this. Does anyone get the reasoning over here? Zaib, is this clear? Aba, Rida?
Um, like if the graph is showing that it's near the
Hmm.
like the the absorption is like near the range of the alcohol, so we can assume that it is forming an
Achha,
alcohol.
exactly. That's what I'm trying to state is that these absorptions, they're not unique. They're not at a very fixed frequency. They already gave you a range, right? But initially I eliminated it because the problem was that it wasn't fitting in the range because its absorption was around 3000, but it was very close to the 3200, 3600 range. Why could the range vary? There could be fluctuation in the range because bonds, uh, the OH bond is not always the same. Okay? There could be other atoms that could be pulling electrons or pushing electrons. There could be an electronegative element to it. So the bonds can always vary. Okay? The polarity of bonds, all OH bonds are not exactly the same. All serial bond O's are not exactly the same. Okay? If there's an OH bond over here, the electrons over here would be pulled by the OH. So so remember, even the carbon and hydrogen bonds are not always unique. Every molecule, the bonding is slightly different from the other molecule. But if you look at the CH bond over here and the CH bond over here in this other molecule, their bond energies are going to be different as well. Because this oxygen over here, this extra oxygen is going to have an effect on the bonds on the entire atom. Okay? So every atom, the bonds are kind of similar, but they are slightly different from each other. Zaib, do you get the point?
Yes, sir.
Achha, so remember for infrared spectrum, now the only problem I eliminated this one was because of this C single O, because I had to put that in. So now the issue is whether this is the correct answer or not. We would have to check. I came up with the last one, D, mainly because there was a C single O bond that was showing up. So we would have to actually check for this because the last OH is still creating some doubts, but we can't really ignore that. Uh, so our best guess is D, but we can have a look at the marking scheme, which is what question is this? Question number 30. T30 is actually C. They're not T30. Is this the same paper? S1912. And this is S1912. They actually went with this one. They actually said this was the correct one. Why did they ignore this one? Just one second. C single O. This is
Saren, why did we consider the second peak from the right?
which one?
The
ये
second
वाली?
peak from the right.
अच्छा
नहीं,
इसके second peak from the left or right? ये वाली, this one?
right. Yes, exactly this one.
अच्छा, remember one thing कि when you do when you do infrared spectroscopy, right? Uh,
Mhm.
you always usually don't really consider much about these peaks over here. This is also known as the fingerprint region sometimes.
Mhm.
Okay, this region is usually ignored because you get a lot of random peaks over here and it's hard to distinguish. Uh, did the question specifically state to ignore? No, it didn't. Now the problem is Now the problem is this peak. Why did I ignore this one? I ignored this one is because it's not a very unique peak. I mean, even if I consider this one and open the data booklet, this is around 1400 to 1500, right? So if I start looking at the 1400 and 1500 range, uh, I'm going to get alkenes. There's nothing at 1400 and 1500. But if I look at this, you get 1400 to 1500 exactly. So data booklet is suggesting that there's going to be an aromatic compound. I mean, this is the closest one, right? So it's suggesting it's serial bond C that's vibrating, right? The problem is I would have to ignore that because in my case there is no serial bond C anywhere in all the four molecules. Ibrar, is this clear?
Yes, sir. Thank you.
So the point is we won't get any information from this one, or we're getting the wrong information. But still, the question is, Yevali peak. This peak was actually quite clearly visible. Initially I did not take this as an OH peak, but this peak was quite clearly visible, the C single O. So my assumption is, Deacon, you can note this down, that the OH peak has to be very strong. Because the data booklet is suggesting that the OH peak has to be very strong. So this was definitely not OH. Why? Because it wasn't a strong absorption, not strong absorption. It wasn't a strong absorption. What is it then? What is the absorption at 3000 then? Because there are other things that are absorbing frequencies at 3000, and that must be this one. At exactly 3000, you have the CH, and it's not the CH peak is not a very strong one. It's sometimes strong. It's also weak. So the OH peak is always a strong one. Uh, and it's much further down the road than 3000. So it wasn't actually fitting with the OH. The OH peak is much further away as well. So which is why the first thing that we did was probably the right one, that we didn't call this as an OH peak. The first thing is it's not a strong absorption. The other one is that it should have been further down the road. So we had to actually ignore the OH. Okay, but still, it's still a confusing question because this is clearly CO. I mean, that's the issue. Okay, this is clearly CO. This is clearly CO. So I'll check the examiner report for this and get back to you. But is the question clear? Otherwise, why this wasn't taken as the OH, or why I think it? Even we were not taking this as an OH peak, right? It was only this thing that was causing the confusion, that there had to be a C single O.
Sir, and how is it 3-hydroxy?
What is 3-hydroxy?
मतलब अच्छा, our answer is supposed to be butanone. सही, ठीक है.
वो तो C होना चाहिए था. But we went with the wrong one, right?
Hmm.
मतलब मुझे OH पे तो I had a doubt on the OH peak, but
So basically, OH is the turning point.
but this thing is still causing confusion.
Sir, and how do we know exactly if it has 4 carbons or 3 carbons? Do we know that
नहीं,
exactly?
नहीं, you don't know. Infrared spectrum provides very little information. ठीक है? You can only barely identify 1 or 2 bonds. So you can't really identify a lot of bonds. Always remember when you're doing infrared spectrum, this is the one that's going to be uniquely identifiable. This one at 1600 and 7. This is the one that's uniquely identifiable, and the OH bonds are also quite identifiable. Apart from that you can't really get a lot of information from an infrared spectrum.
सही, ठीक.
And especially this part over here, the fingerprint region, this doesn't really give you a lot of information. It's just random. Most of them are random absorptions. Okay. So the first thing is you would have to look for these absorptions. So moving on, the next one. The next one is, so I'll get back to you on the examiner report about the C single O. So when O2 reacts with H2S, the product are SO2 and H2O. Mixture Y contains an equal number of two molecules and no other molecule. So O2 reacts with H2S, and the products are SO2 and an equal number of the two molecules shown. I mean, these two molecules, talking about these two molecules. An equal number. So equal number, what's the average MR in Y is? And this is the mixture. What is the average MR? So the molecule has a mass of, what's 18 plus 16? That's 34. And what is 32 plus 1 plus 1? That's 34 as well. So the average MR is going to be 34. Because the first option is correct. If some oxygen molecules are removed from Y, the average MR of the mixture remains the same. That is also true. Like if you have, I mean, even if you remove this, the average MR would basically still be 34. So that's correct. When mixture Y is ignited, some H2S remains unreacted. Is that correct or not? So he's assuming that what would happen if H2S reacts with O2? They're going to produce, what would there's going to be H2O getting produced, and there's going to be SO2 that's going to be produced. And you can balance this equation. If you try and balance this equation, it's going to be the H and S are balanced. You can balance the oxygens. You have to, I think, double this. 2H2S, so that's 2H2O, and there's 2SO2. How many oxygens do you have? That's 2 plus 4, that's 6. So there's going to be 3O2, right? So the question is, when the mixture is ignited, now remember the mixture has equal number of moles of H2S and O2, but in the equation they're reacting in 2:3. So if I have, let's say, if I have 3 molecules of O2 and I have 3 molecules of H2S, which one is in excess according to the equation? And what would, ठीक है, तो इसका मतलब है H2S is the one that's in excess, because you don't need 3, only 2 are needed in the reaction. 1 molecule would be left at the end of the reaction, right? So H2S would remains unreacted, some H2S, and that is correct. ठीक है, is this clear, Rida? Hiba, is this clear? Tala, is this clear?
Could you explain how point 2 is correct?
Which I couldn't hear you. Can you repeat?
Could you explain how point number 2 is correct?
Can you type? Can you type your question? As a point 2, 1 second, what's point 2? If some oxygen molecules are removed, the average MR of the, I mean, let's assume that you had 1 molecule of oxygen and you had 1 molecule of H2S, right? This is 34 and this is also 34. Both of them are 34. So he's saying so let's say our mixture had exactly 1 molecule of this and 1 molecule of this. Both of them are 34. Take the average, it's going to come out to be 34. If you remove some of the oxygen molecules, he's talking about the oxygen molecules. So let's say I remove the oxygen molecule from the mixture. You're only left with 1 molecule of H2S. What's the average MR now? It's still 34. Abba, is this clear? Okay, so it's still coming out to be 34. That's the next one is, why is this? Just 1 second. As the next one is, there's a molecule of TC are correct. You can pretty much do this on your own. It's you can figure out the number of nucleons, etc. Just remember nucleons, when he mentions nucleons, that's protons plus neutrons. So you can hopefully do this on your own. As the next one, in which reactions are nitrogen atoms reduced? What's the oxidation state over here? +4. It's with 2 oxygens. And what's the oxidation state over here? That's 0. So that is reduction. So next one, this is, I said everywhere there's +4 and +4. So what's the oxidation state in N2O? That's, I think, +1 because O is -2. What's the oxidation state over here? That's -3 because H is +1. So I think in all of them, they're getting reduced. Okay, they're getting reduced in all of them. I said next one is the manufacture of ammonia from nitrogen and hydrogen is an important industrial process. Which of the following would leave the equilibrium constant Kp for the formation unchanged? So, which of the following would leave? What are Kp and Kc affected by? Can anyone tell
Temperature.
me? Okay, they're only affected by one thing, exactly one thing, and that is temperature. So adding an iron catalyst would not affect Kp. Addition of ammonia is not going to affect Kp. Increase in pressure is not going to affect Kp. What's going to happen is that even if you try to change the ratio of the products to reactants, okay, every time what would happen if you add more ammonia, the ammonia would increase, the equilibrium would shift backwards, and it would simultaneously increase the N2 and H2 as well. So the balance would be maintained. The same would happen for pressure. Adding a catalyst would have exactly no effect on the equilibrium position because both forward and backward reaction would be speeded up at the same time. So it's only temperature that's going to affect Kp. Otherwise, Kp is not affected. As a Piragla, which reaction involving calcium and its compounds produces two gaseous products? So first thing, what is going to be produced when calcium nitrate is heated and decomposes?
I think nitrogen dioxide and oxygen. मतलब they're two gases.
Okay, so two gases are going to be produced. So it's going to be CaO plus NO2 plus O2. Calcium carbonate, what would be produced when you decompose this? So it's going to produce just one gas, right? That's going to be carbon dioxide. What happens when calcium reacts with water? So you have calcium hydroxide getting produced plus H2 gas. So there's one gas, just one gas. So these two options are incorrect. Only the first one is correct. And remember, if the second is incorrect, you don't even have to check the third one. The third one is also incorrect. Okay, the next one is a small quantity of hot concentrated sulfuric acid is added separately to solid samples of potassium halides. Which potassium halide reacts and produces a mixture of products which include this one? So just a quick revision. Okay, what did you study in What did you study in organic? Where's your just a quick revision of this. Okay, in organic, you've studied is group 17. This is group 17. I say in organic, you've studied when you talk about halide ions, you've studied that down the group it becomes easier to lose electrons. I-1 is a pretty good oxidizing. It's a pretty good reducing agent because it loses electrons very, very easily to form I2. So the bottom ones, I-1 and Br-1, they're pretty good reducing agents. The top ones, F-1, smaller atoms, it's more difficult for them to actually lose electrons. Cl-1 likes to gain electrons, doesn't really like to lose electrons. So they don't like to lose electrons. The bottom ones, they like to lose electrons. So the reactions with concentrated sulfuric acid, you have to remember the first two, NaCl, nothing much happens, only displacement happens, and HCl gas is produced. There is no redox reaction. So only displacement happens. But when you move down the group, Br-1 and I-1, they're pretty good reducing agents. And they're going to reduce H2SO4 to SO2. And bromine is going to be formed. NaI would also get involved in a redox reaction. There's going to be displacement, but there's going to be simultaneously a very strong redox reaction happening. And I-1 will get oxidized to I2. And sulfuric acid, where S is +6, will get reduced to sulfur dioxide, where S is +4. Or it could get reduced to sulfur, solid sulfur. Yellow solid would be produced, where S is 0. Or it could be produced into this rotten. H2S has a smell of rotten eggs. That way sulfur is -2. So reduction of sulfur is going to happen because I-1 is a pretty good reducing agent. So coming back to the paper, it's this one that's not going to react. Cl-1 doesn't really like to lose electrons. Okay, it's not interested in losing electrons. Doesn't really like to do this. Okay, this is not going to happen. But I-1 and Br-1, they're pretty good reducing agents. They would like to lose electrons, and sulfur would be forced to gain electrons. ठीक है, clear है? अच्छा ये business clear? चलो ठीक है. अच्छा diagram
Yes, sir.
shows a compound used as a flame retardant. Which statement and structure are correct? The empirical formula, just try and figure out the empirical formula very, very quickly. The skeletal formula is given. So these are your carbon atoms. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you've got 12 carbons. You can count the bromines. That's 6. 1 second. So you've got 6 bromines, and you can count the H. That's 2 over here. There would be 2 hydrogens over here. This one will have 1H. 1H. Each carbon should have 4 bonds. 1H with this. 1H with this. 2 H's with this. 2 H's with this one. 1H and 1H. Now count the number of hydrogens. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So you can divide everything by 6, and you'll get C2, and H would be 3, and Br would be 1. So that makes perfect sense. So it's C2H3Br. And then he's saying that the C12 ring, so there are 12 carbon atoms, is not planar, which is also correct because around the carbon atom, the bonds are tetrahedral because all of them are making single bonds. So they're going to be like this. So for example, if I look at this carbon atom, then it's bonded to a Br, it's bonded to an H, and on two sides there's the carbon chain. So the bonds are either going into the page or they're along the page. Then this carbon atom would be tetrahedral as well. So it's going to have bonds in a tetrahedral arrangement. So the next carbon atom is also, it has one Br, one H, and this one would be another carbon chain. So all of them are tetrahedral, so they're obviously not in the same plane. The next is there are 6 chiral carbon atoms. Do you have 6 chiral carbon atoms? 4 different. I mean, this one, 4 different groups, I think. Which looks to be correct.
Every carbon with a bromine is a chiral carbon, though, with 6.
So they're all chiral. All 4 sides are different. Okay, even though it's a cyclic structure, but this side is different. The bottom side is different. Udhar CH2 CH2 aa raha hai, yahan pe there is CBr, so that is different as well. So let's move to question 38, which is halogenoalkanes can be hydrolyzed using aqueous sodium hydroxide. Which compounds tend to be hydrolyzed by an Sn1 mechanism? So पहले तो जल्दी से let's I think I have halogenoalkane somewhere. वैसे बता दो which one is Sn1 mechanism for a halogenoalkane?
Primary alcohols, I guess.
No, not primary alcohols, tertiary alcohols.
Oh.
Not alcohols, halogenoalkanes, ठीक है? अच्छा, this is Sn2. Sn2 is for primary. ठीक है? Remember, Sn2 is for primary. The OH minus one is going to come in and it's going to attack the carbon positive because it's a polar bond. It's going to directly attack it. Why? Because the carbon is very strongly positive. Why is it very strongly positive? Because there's not a lot of carbon chains around it. So it doesn't have a lot of electrons around it. H ke paas there's only one electron with H. Doesn't really have. So the positive charge is not its charge density is pretty high. So the OH minus one is very strongly attracted to it. And because the positive charge density is very high, it wouldn't allow the Cl to leave or break off unless the OH minus one comes in and pushes the Cl away. So this is what the OH does, and that's why the Cl breaks off. But in an Sn1 mechanism, what would happen is that the carbon is surrounded by carbon chains, large groups. So in that scenario, what happens is that the Cl is able to break off on its own. And why is it able to break off on its own? Because the carbon is not very strongly positive. So it's not attracting the Cl negative that strongly, because even if it becomes positive, it can gain electrons from other places. Like it can gain electrons from the carbon chains. So it's capable of doing that, which is why the Cl is capable of taking away electrons easily. And the Cl takes away electrons. And because the carbon doesn't have a very strong positive charge, the OH is not interested in this carbon initially. But once the Cl leaves, there's a positive charge over here, and the OH ion concentration, if it's high enough, would come in and bond with it. So it's a two-step reaction, and it happens for tertiary halogenoalkanes. And it's an Sn1 mechanism because the rate of reaction depends on only one of the reactants, which is the halogenoalkane. Because I explained to you, if you speed up the fast step, the overall speed of the reaction is not going to be affected. Like if this takes 100 seconds, this takes 1 second, and you increase the OH ion concentration, the 1 second part increases, speeds up, and takes 1 microsecond. The overall speed is hardly affected by the reaction. Okay. So coming back, we're looking for kya tha question? But what was our question? It was Sn1 mechanism. So tertiary halogenoalkane. So it's this one is correct. This one also kind of looks correct. This one is definitely not correct. So I'm just going to look at this carbon atom, and this one is a tertiary halogenoalkane. Look at the carbon that has a tick mark on it. So there's a carbon. On one side there is a CH2 and a CH3. Okay, so there's a CH2. It has a CH3 in a bracket. That means it's a branch. It is attached to a Cl, and then after that it is attached to CH2 CH3. So it is definitely a tertiary halogenoalkane. You can also look at the next one. That's also a tertiary halogenoalkane, because if you look at the C that I've marked, on one side there is CH2 and CH3, and there is a Br, plus there's a CH3 in brackets. That means it's a branch, and followed by CH2 and CH3. Okay, so that's also, this one is not, because if Br is right at the end, it would have 3 carbon chains next to it. So we can, before doing 39, we can do 40. An oxidizing agent that can oxidize ethanol to ethanoic acid, or ethanoate ions will also oxidize methanoic acid to carbon dioxide and water. Which reagents on heating will react differently for methanoic acid and ethanoic acid? So now, first thing, he's talking about differently. They're both acids, right? This is an acid, this is an acid. So carbonates would react with acids. So both of them would react with acids. So that means one is not an option, so 2, 3 are automatically. They're automatically correct. And they were saying that oxidizing agent that can oxidize ethanol to ethanoic acid will also oxidize methan. So he's talking about ethanol. He's talking about aldehydes. He's talking about oxidizing agents that oxidize aldehydes. So felling agents, it's going to oxidize aldehydes. KMNO4 would also oxidize aldehydes. Uh, so he's saying that anything that oxidizes ethanol to ethanoic acid will also oxidize methanoic acid. So methanoic acid is the only one that's getting oxidized. Ethanoic acid we did not study. There is no oxidation. But he's saying that methanoic acid is going to get oxidized. Hence 2 and 3 are the correct option. ठीक है, clear?
Yes, sir.
Yes, sir.
Baki, you can do the yield question on your own. ठीक है, we're running out of time. Just try and figure out the conversions are given. You can figure out the yield yourself. Like how many moles is this? It's 74 divided by 74, mass divided by MR. ठीक है, you can draw butane 2-ol. The MR is 74. So that means mass divided by MR, that gives you 1 mole. Now 1 mole of butane 2-ol should produce exactly 1 mole of butanone, right? According to the ratio, 1:1. Theoretically, these are your theoretical moles. But he's saying that you're getting 44.64 grams of butanone. So 44.64. Butanone is CH3. What is butanone? C2H4O2. Needs C2. Need butanone. But is 4. C4. H8 and O. So क्या होगा? That's 4. That's 48. 48 plus 8. 48 plus 16. What's 48 plus 16? 64 plus 8. 64 plus 8. 72. Can anyone tell me how many moles is this?
Zero point 0.62.
So 0.62 moles. So the thing is, you're getting 0.62 moles. These are your actual moles. Theoretically, you should be getting 1 mole. If there's a 4 carbon atom thing, you should get a 4 carbon atom thing. If it's 1 mole, it should be 1 mole of this. But you're getting 0.62 moles. So what's the yield? That's 62%, right? Okay, the actual is this one. The theoretical is this one. So you can do this with all of them, and you can find the yield. We're done with this paper. We're going to continue with a new paper next time. Okay then.
Sir, thank you, sir. Allah Hafiz.
Allah Hafiz.